Hello and welcome to the Ask Echometer weekly training sessions. Today's session is titled Introduction to Plunger Lift and will be presented by Lynn Rowlan. During Lynn's 40 years in the oil and gas industry, he's received several awards for his work. He's authored more than 80 research and technical papers, co-authored a book on gas well deliquification, and he holds a patent on plunger lift analysis. He's given hundreds of seminars and talks on efficient operation, optimization, and troubleshooting oil and gas wells, and we're so glad he's presenting today. So Lynn, I'll turn it over to you now.
Well, thank you, Carrie Ann. Good afternoon, or in fact, good morning, depending on where you're logging in from. So this is kind of fun to have people from all over the world on this presentation. The class, this is going to be about an hour talk. It's on plunger lift. Echometer began developing this technology a little bit after 2000, almost 20 years ago. And it took us a little bit to come up with a software program. May 18th, 2005, we had our first plunger lift software program and first class on analyzing wells with acoustic data on plunger lift. So this is if you're familiar with TWM, that was what we used at first, and now we've migrated the calculations and software analysis into a program called TAM. You can download the TAM software from our webpage. You can use that for no charge to import your TWM data if you track a plunger and analyze it in the TAM software. It has some additional features that make the analysis easier and better in my view. I've listed several articles here, several papers that were written. Those papers are available. They'll likely be on a link on our webpage. So that'll be once you download or go to the webpage, the Ask Echometer webpage, you should be able to access these papers, or they may just be on our technical paper webpage. Plunger lift is a method that's used to typically deliquify gas wells, and it's probably the most economical lift method because the cost to set the equipment up is low cost. The cost to maintain the equipment is low. You don't have to use a rig to install it typically. And the deeper the well is, the deeper the casing for a conventional well, the more casing angular volume you have, which means you have more energy. So it's not really more cost versus depth. You just limit your number of trips because it takes more time for the plunger to travel. The plungerless system for a conventional well uses the energy from the well, and so the cost for operating costs for energy can be zero if there's no additional gas is added. Probably the biggest disadvantage of conventional plunger lift is that you have to shut the well in, let the plunger fall to the bottom, and let the pressure build up so it'll come back for the next cycle. The plunger lift, typically conventional plunger lift is gassy wells. And to get the liquid out of the tubing, you can sweep the tubing and remove any deposits, but often you don't have a high liquid rate. So it's a lower liquid rate producing method, but it lacks gas. So and there's kind of an argument which method can get the pressure to the lowest. And someone would say, well, you can run a beam pump and pump the well off, but if you don't put the pump at the bottom of the purse, then a plunger lift can probably even do better than beam lift. So beam lift doesn't always have the lowest pressure. It depends really where the pump set depth is compared to the end of the tubing. Now, probably the first thing you do when you go to a plunger lift well, if you're going to track the plunger, and we'll talk about how that all works, is you're going to shoot down the casing and then shoot down the tubing and see what you see. And what I mean by that is if the well's having problems and you're wanting to troubleshoot that well, then this acoustic trace here shows that there's an obstruction, some kind of obstruction in the tubing, and the liquid level has been pushed out of the tubing, and the tubing is dry, and you can see upkick there and a downkick at this obstruction. This obstruction is something in the well that you're not sure what it is, but it's gonna maybe block the plunger as the plunger falls down the well, and you'll see that by shooting a fluid level, and then you'll have some expectation of what to see when you track the plunger. Now this is another plunger lift well, and the plunger was coming to the surface only about 20% of the time, and so the operator caught the plunger and shut the well in overnight. He came back in the morning, he shot the fluid level, and he could see the upkick at the hole in the tubing, and a downkick, liquid still in the tubing, above the tubing. So he could see what's wrong in both of these fluid level shots, and it helps you understand what to expect and how to potentially, what kind of look for when you're shooting and tracking a plunger. They help each other analyze the well. This just shows some of the basic components of a plunger lift system. You know, the controller is the computer that operates the system, and it may be simple, it may be complex, and the motor valve is opened or closed by the controller, and the controller is using some settings to decide when the well is turned off or shut in, and the plunger falls to the bottom, or when the motor valve is open, the well's on, and the gas and the plunger and liquid are brought to the surface or held at the surface in afterflow. Then at the surface there's a lubricator, and it's designed to catch the plunger. It has a spring in it. But it's important, even if you have a spring in the lubricator, you don't want to run the plunger dry, or it's going to cause damage. So it's important to always have a little bit of liquid above the plunger, and you want the plunger to hit the bumper spring on the bottom and have liquid there so it doesn't cause mechanical impact and potential damage. Now the arrival sensor is typically right here, and it'll detect the arrival of the plunger, and there's different types of sensors that you can have and different types of transducers you can have to measure pressures and arrival velocities, arrival of the plunger, and all those are used as input into the controller to operate the well. The plunger is a mechanical seal, and it seals the liquid above the plunger and the high pressure gas that drives the plunger to the surface below the plunger. And so again, it's a very simple system. It's low cost, and it's typically efficient. This is a list of components, and this is the components that are used to set up a plunger lift installation, and this is actually what's used by a company. And if you go through this list of components, most of the components, other than the bumper spring, the plunger, the controller, the motor valve, and the lubricator, the rest of it's just pipes and valves. It's pretty simple to set up. And so you know it's not a heavy piece of equipment you have to move on site. It mainly just needs to be assembled, and then you can set the bumper spring and drop the plunger and follow the plunger down to the bumper spring and see it come back up. This is the Echometer equipment, the wired equipment on a well, and we can use both the wired and wireless equipment now to track a plunger. And this is a fairly old picture of the gas gun on the lubricator, and I like to show this picture because when we first started tracking the plunger, we'd attach the gas gun directly to the lubricator, and we have to close the master valve to bleed this pressure off so we could attach the gun, and that would take some time, and often it would extend the shut-in time, and that would cause the plunger to have extra casing pressure, and the plunger would come up somewhat dry, often dry and too fast when we first started doing this. And I'd wonder why would the operator operate the plunger like that, until I realized it wasn't the operator, it was me, the way I was installing the gun. So we started from then on saying, well, from now on, you need to put a fully opening valve on the well and the lubricator so that you can sneak up on the well. Well, you can't sneak up on the well, but sneak up on the well and attach the gas gun to the well without the well even knowing you're there, and then you can open the valve and start acquiring the data without disturbing the normal operating conditions of the well. So this is how we recommend, the upper left-hand corner picture is how we recommend attaching the gas gun to the well now. we recommend always using a fully opening, typically a half-inch valve, so that we can have it closed and then attach the gun and then open and start acquiring data. And that's really the best method. And we like the gun to be vertical, so any liquid that unloads, it runs in and it runs right back out. It doesn't fill the gun up with liquid like it would here if it was just laying on its side. Now, when you collect data on a well with an Echometer system, there's a paper that we wrote in 2000 called Total Well Management, and part of that paper said, here's the questions you should answer when you use equipment to collect data on a well. And so for plunger lift, you can see your questions are, where's the plunger? Is that the surface or in the liquid or on the bottom? And you can see that. You can see when the plunger hits a liquid, and that basically a gassy fluid column hits that gassy fluid column. You can see when the plunger hits it. You can see the pressure based on the casing pressure calculated down at the end of the tubing. And you can see the potential shut-in pressure based on analyzing a conventional cycle. We can see the liquid above the end of the casing, above the end of the tubing in the casing annulus. We monitor the tubing and casing pressures throughout a cycle, and that provides a lot of different information that we'll talk about. We can see that if the well needs a standing valve, because during shut-in, if the liquid load in the tubing gets pushed out, you need a standing valve to keep that from happening. And that usually occurs when the tubing's set too high and you just don't have any pressure from the well to hold the liquid in. We calculate the maximum production rate available from the well. We use the casing pressure, the tubing pressure, the casing size, tubing size, and the liquid in the tubing to calculate how much gas is stored in the casing annulus, stored in the tubing, flows in from the formation and flows down the sales line. And that's kind of a novel thing that we do. The plunger, when it falls down the well, it not only tells you where it is, what color it just went by, it tells you the distance based on the average joint length of the tubing, and we time it so we know the velocity of the plunger, and then we know also based on the acoustic velocity of the plunger falling the well, we know the gas gravity, so we know pressure, temperature, and acoustic velocity, so we can calculate the gas gravity of the gas in the well. And when there is a restriction, like a down kick, that reduces a cross-section of the tubing, that's likely to stop the plunger, and we can see when the plunger stops. So that we'll see all those kind of things when we talk about the data. Now this is a typical plunger lift conventional well cycle. And it's one of the examples called plunger normal cycle. And so here we shut the well in, and you can see the green is the acoustic signal, the pressure signal for the tubing, and the blue is the casing pressure signal in blue. And when we shut the well in, the casing pressure and tubing pressure are building up. And in the background, this dark black signal here is the acoustic signal, and so the pressure is building up because pressure, gas volume is flowing into the tubing, and the plunger's falling. This is noise of the plunger falling down the well. And when the plunger hits the liquid, we see a signal change right there where it hits liquid, and then we see another signal change right there. It usually gets quieter. It may get noisier when the plunger hits the bottom, depends on the well. And then we see the end of the shut-in time period when the motor valve opens. We see the acoustic signal when the plunger unloads, the tubing drops the line pressure and brings liquid to the surface. We see this noise here that is the liquid rushing by, the gassy fluid rushing by the microphone. We see the pressure response of the tubing as that casing pressure gets closer and closer to the surface as it unloads the liquid and the plunger to the surface in the well. And then this piece right here is the afterflow. Once the plunger rises to the surface, the plunger is held to the surface, and the well continues to flow. Now, the motor valve, this is the motor valve, and it's controlled by the computer, the controller on the well. And so it's really the switch. It's the on and off switch for the well for a conventional plunger. And when the controller says shut, then this valve closes and no more flow goes down the sales line. And the pressure in the well starts to build, both in the tubing and the casing. And the plunger during this off time is falling down the tubing. And then when the controller sees a certain set of conditions based on the control algorithms that are set in the controller, then the motor valve is opened by the controller and the well is on, like an on and off switch. And then the gas liquid is unloaded from the tubing, and gas is surging out of the casing into the tubing, and the well unloads the liquid and then holds the pressure at the surface when the plunger at the surface when the plunger arrives. Now the controllers, there's all kinds of controllers, and the simplest one is typically time. And a lot of times when you use when you use a manual on and off timer, the operator often is concerned the plunger comes up, and often he'll say something like, if my plunger comes up, that's good enough. And what that means, though, is that means that often the well's not optimized. So when I see a well that's on a manual timer, plungerless well manual timer, I often think that it's probably not optimized, and more gas could likely be produced from that well. The next type of automation here is called based on plunger velocity, and it needs a good arrival sensor to see the arrival of the plunger, and that then you can adjust the arrival speed by changing the amount of afterflow. More or less afterflow can regulate the rise velocity of the plunger. And then there's combination type controllers that are more complicated. And the main thing the controller purpose is it should help you maximize your production out of the well. Now, when I talk about plunger lift cycle, I'm thinking about a conventional plunger cycle is divided in three parts. The well is shut in by the controller shutting the motor valve, and it's shut in for a sufficient time so that the plunger can fall from the surface all the way to the bottom to the bumper spring. And during that time, we want the casing pressure to build to a pressure that's high enough to bring the plunger and accumulate liquid back to the surface. So that's what I call the shut-in time. And in fact, that's the first time it's defined to me by Dan Phillips. I've stuck with that definition. Unloading means that some criteria has been met in the controller, time or pressure or something, maybe whatever the conditions are met, the motor valve opens and the casing pressure starts to drop and the tubing pressure drops, and that stored energy in the casing results in lifting the plunger and accumulated liquid to the surface. Once the plunger arrives, we're in afterflow and we're selling gas down the cells line, and the plunger is typically held at the surface by pressure. And so that's the three parts of a plunger lift cycle. Now this is just a little simple diagram that shows the plunger lift well and the plunger in the well. Here we're shut in, the plunger's fall on the bottom, it falls through the gas, it falls to the liquid, it rests at the bottom. Once it's at the bottom, the casing pressure is increasing to a point where you're ready to bring it back up. When those conditions are met, then the motor valve opens based on the controller, and the plunger with the pressure from the casing is driven to the surface, and the plunger then is held at the surface once it arrives with pressure, and then we're in the afterflow time period, and then the cycle repeats. Now this is the same data we looked at a minute ago. It's called the normal plunger cycle, and we've labeled here the casing pressure, we called it CP, and the tubing pressure called TP, and the line pressure called LP, and those are just abbreviations for LP for line pressure, TP for tubing pressure, and CP for casing pressure. And when you open the valve to bring the plunger up, a rule of thumb is called the load factor. And the load factor is the ratio of this distance here, which is casing minus tubing, compared to this overall distance called the casing minus line, which is the lift energy. And so this distance here should normally, by rule of thumb, be less than half this distance. And so if you look at your casing and your tubing pressure plot at the end of shut-in, and you look at your distance to your casing minus line pressure, and this distance here is more than half the distance, then usually the plunger won't come up. You usually have to have a smaller distance, a smaller liquid load. So this well has a liquid load probably around 20%, and the plunger will come up. So if we open the valve here, the plunger comes up, and sure enough, it came up in this well. And load factor is just a method that you could use for control if you wanted. This just talks about what we just said. The casing pressure is what builds up during shut-in, and you may even need to build extra time to have enough pressure to bring the plunger up. There's a paper that we wrote called Floss and Gall that calculates the rise velocity based on a certain casing pressure, and that's available papers on our webpage. Unloading is here is talking about when you open the well up, the tubing pressure drops the line pressure, and that creates that differential pressure. And then the casing pressure minus tubing pressure is the liquid load, and that casing minus line is the energy that lifts the plunger to the surface. And so these pressures are something that we need to consider when we operate the plunger lift well. Now this is the example inside the TAM software where the motor valve is open. Right here, the motor valve is open and the motor valve is closed right here. So this is our shut-in time period, and this is unloading and then after flow. And so during this time when the valve is closed, there's no sales, the plunger's fall on the bottom, and the casing pressure is building up to some limit. And this data has been captured by the TAM software or the TDM software, and this is the analysis tab inside the TAM software to define a cycle. And so here we have A, which is where the valve closes and shut-in begins. Point B, this dashed line right here, is when the valve opens and unloading begins. And this is where the valve closes and the next cycle begins right here. And these are the actual clock times of those events. And we can click on this word clock and change that to minutes, seconds, hours, or clock time. So there's different ways to show this data, and you choose which way you want to show the data and make your reports and things like that. Now this is the unloading portion of the cycle, and so here we have the motor valve opens right here at B, and then the tubing pressure drops to line pressure right here. And at this point, the line pressure would be when the liquid starts to arrive. Right here, it says the liquid starts to arrive at a tubing pressure of 126 psi, and the casing pressure right here has dropped down to about 235 psi. So that's a drop from about 258. No, it looks higher than that. It's from about almost 300 psi down to about 258. That's when the liquid starts being brought to surface, and all this noise here, that's noise. The black noise is a liquid going by the microphone of the gas gun attached to the lubricator, and we're hearing this. We're recording these signals at the surface of the well. Here's the tubing pressure increasing, and the plunger arrives right there at that little spike. Typically, almost always, there's a little spike in pressure. When the plunger arrives, the casing pressure sort of flattens out right there. And this is the liquid unloading at the surface. And once the liquid unloads, the plunger is then held at the surface. And after flow, and after a period of time of after flow, then the cycle repeats. I think we just said all that, so I'll skip on the next slide. Now this well right here is the plunger well 3 cycles from static. And so what we're saying here is there's 1, 2, 3 cycles. And here we're shut in, and the casing pressure is 600 psi, and the tubing pressure is 500 psi. And for people all over the world that are not U.S. units, you can modify the display units to any system units that you wish. You just have to go into the settings and say metric or whatever systems you want to choose. And if you click on the heading here, you can change the heading of the graph. And the units right here on the screen, you can click on that and change it. Notice here that the elapsed time is in minutes. So the tubing pressure minus the casing pressure minus tubing, 100 psi. 100 psi in 2-inch tubing is about 250 feet of gas-free liquid, and it's about 100 psi, 250 feet. Now, that's a rule of thumb. It's approximate. I use those numbers because they're easy for me to remember. So I think about a barrel, it's 100 foot, 250 foot tall, 100 psi. So we just got a barrel of liquid right there. Now, right there at point A, we manually open the well up and we start dropping the pressure, and the plunger and liquid start to arrive, and we start seeing this unloading of the liquid. And there's a lot of time goes by here, a lot of liquid's being brought to the surface, and then right there the plunger arrives, and immediately we shut the well in because we're just trying to swab that liquid out and drop the plunger. And so here's the plunger falling back through the gas, here's falling through the liquid, and then right up there it's on the bottom. And then we open it back up, and notice now this time that there's less time here, less liquid. And then as soon as the plunger arrives, we shut it back in, another cycle. And then the liquid's less, and now we're ready to turn the well onto the controller and let it continue to operate. So these 3 cycles show quite a few things. We'll look at this in a little more detail. So here's an annotated plunger normal cycle, unloading and afterflow events. The casing pressure drops when you start unloading. The tubing pressure drops. The pressure drops down to line pressure. When the plunger liquid starts to arrive, the tubing pressure goes up. The plunger typically arrives at the peak pressure. The noise of the microphone increases significantly when the liquid goes by the microphone. Once you see the spike, almost always the tubing pressure starts to drop, and casing pressure starts to drop in afterflow. So this is a normal behavior of a conventional plunger lift well in unloading and afterflow with the data that you'd collect, let's say at high speed, at 30 samples per second or faster. And so usually on a padded plunger, you'll collect data at 30 samples a second. Maybe a solid plunger, you'll collect data at 60 samples a second because it's faster. And then at a bypass plunger or 2-piece plunger, you may even go up to 480 samples a second to be able to see the plunger falling so very, very fast. So being able to see the plunger, it kind of takes your guess time out of the time. It takes your guesswork out of the time to set the time for shut-in. You can typically see the plunger fall to the liquid and then rest on the bumper spring. Probably 60% of the time you can see it hit the bottom and see it bounce on the pressure transfer to the bumper spring. You'll maximize your gas production from your well if you have the minimum shut-in time required to get the plunger to the bottom. We won't talk about Fossengal in this presentation, but we will talk about that in a future presentation. You can use the Fossengal model to set the shut-in time to bring the plunger up at a certain rise velocity, and that's available in an Excel spreadsheet. If you're interested in that, you can email us and we'll send that spreadsheet to you. Plus, you'll save some time by making sure your plunger runs are made, and you'll maximize your sales. Now, this is the example of the second cycle that we saw. Let me go back just for a second. If we're looking right here where the well is shut in, this is what we're looking at, and this data is acquired at 30 samples a second, and it's 130 minutes of elapsed time. So I'm going to zoom in and look at this piece from this time to that time for more detail. And so that's what this slide shows right here. And so when you look at more detail at this slide, you can see that these little spikes here are fairly uniformly spaced, and those little spikes is the plunger falling through the gas in the well, and we can hear the plunger falling by each of the tubing collar recesses in this EUE tubing. And we calculate the average fall velocity through the gas for this dual pad plunger is 201 feet per minute. And the plunger is falling through the gas, and it hits the liquid right there. And then maybe 10% of the time you can see it fall past every collar below the liquid level. So here we're seeing it fall, especially when the pressure's high. When the pressure's high, the signal carries well, and so the pressure is fairly high here. That's 400 psi pressure on the tubing, and so it conducts the signal very well. And so here we can see the plunger falling past each of the tubing collar recesses in the liquid, and then we can see it hit bottom right there. And there's some other things we can see that we'll talk about later. But the fall velocity through liquid in this case was about 40 feet per minute. And that's a pretty good number. Most of the time when you think about how fast the conventional plungers fall, when there's a seal, the plungers typically fall around 40 feet per minute through liquid. And that's what you should expect to see when you're tracking a plunger. If there's a bypass that opens up and lets the plunger fall faster, it'll fall a little bit faster through the gassy fluid. Now, if we take this data and we zoom in even to a closer detail to 1 minute of time, I know we're looking at 1 minute of time, and this is a normal plunger cycle, and we're looking at the time from 41 minutes of time to 42 minutes of time. And what we're seeing here is that this spike right here is the spike of the plunger going by the 207th joint from, that's the acoustic signal, of the plunger going by the 207th joint in the well. And down here is the table that shows that information. That's the time to that joint. That's the fall velocity from over this time right here. And then that's the depth to that joint. And here's the average fall velocity in this well. And that's the fall velocity we calculate through liquid. And so this little graph shows all these different measured plunger fall velocities versus time. It shows the fall depth through, there's depth here, depth through here to the gas, and then depth through liquid. And it shows the plunger at liquid at that depth and the plungers on bottom at that point in time right there. And if we click on this arrow here, it'll expand this graph and we can see it in more detail. So how do we get the fall velocity? Well, it's really just as simple as saying here is the time at this caller echo, and here's another time at this caller echo. So this is 5.663 minutes and 5.802 minutes, and this is the elapsed time if you just take the difference, and you know the average joint length, so you can calculate the distance as average joint length divided by the change in time, and that gives us the fall velocity through joint 21 through 22 caller, and there's our average fall velocity. So this is a view of 1 minute, and this is what we're looking at right here, 1 minute, and we can even make it a smaller interval if the plunger's falling faster. So we may even need to make this interval more than 1 minute. And here it shows what minute we're looking at, or the time interval we're looking at right there. And this is the total time right here that it falls through gas. So this is the time through gas, and that's the portion of the time you're looking at where it fell through 1 minute time through the gas. Now we click on that button right there, and that button pops up this screen, and this screen is the plunger fall velocity versus depth. And you can see that it starts out fast. Fast is more negative, falling down. Minus means falling down, and more slow means that it's less negative, so it's falling down 140 feet per minute right here, and it's falling at 240 feet per minute right here. And so for a normal plunger well, that there's no hole in the tubing and the casing's building up during shut-in, then the plunger tends to slow down over time. And so this is the plunger slowing down over time, and so that's normal. And we were able to monitor this and monitor the plunger fall in the well. And at first I thought, well, that's just normal. And then I realized that it's not normal. It's just a function of how fast the gas flows in the well and how fast the pressure builds up. And we wrote a paper on that, and that's one of the papers that's cited at the front of the SV paper cited at the front of the document, the front of this presentation, where we have a model that calculates the fall velocity as a function of this inverse square root of the density of the gas. So as the gas pressure goes up, the density increases, and then the velocity changes inversely proportional to the square root of the gas density. So that's this relationship. So here's the depth scale, here's the velocity scale. You can click on any point and it shows that point up on the top, and it rotates the table back to that point. So if you click on that point, if you were to go back to this table, you'd be on that point in the table. This just shows the shut-in time period, and what we see here is that when you shut the well in, the casing pressure is building, the tubing pressure is building. We typically see these uniformly spaced collar echoes that we can count. When it hits the liquid, the signal changes. Now, I used to say it got noisier, and this Well, here it got noisier when it hit the liquid. And the reason why it got noisier is because the tubing pressure is building up because the gas is flowing in the tubing, and once the plunger falls, when the plunger's falling through the gas, you can't hear the gas bubbling through the liquid at the bottom of the tubing. Once the plunger hits the gassy fluid, and the plunger's below the liquid level in the tubing, then you hear the gas bubbling out of the liquid, and it gets noisier. But if the tubing pressure is flat, that means no gas is flowing in the tubing. And when the plunger hits the liquid, it gets quieter. So and then the plunger on the very bottom, right there, you see it got there, it gets quieter. So there's some things you can see about the cycle you try to analyze as well. Now I'm going to zoom in to 5 minutes of time. So here I'm not marking off 5 minutes of time along the shut-in time period of the entire shut-in time period for this well. And now this is what we see when we zoom into 5 minutes of elapsed time. We can see something that we may not have expected. Right here, the motor valve closed, and it took a short time for the pressure to build up. And once the pressure built up equal to the way the plunger divided by its area, which is about 3 psi, then the plunger falls out of the lubricator right there. The plunger falls out of the lubricator, and that's when it starts to fall. But really, shut-in began right there when the motor valve closed the valve. And see, notice how it got quiet here. It gets quiet when the motor valve closes. And you can see the signal on the acoustic trace, the change in pressure when the plunger goes by a collar. You see the change in pressure on the pressure trace also. So you can see the plunger falling both on the acoustic signal, the change in pressure signal, or the pressure signal if you have a high resolution, high speed sampling pressure transducer. So that's what we have here. And you can see both the uniformly spaced collars on the tubing pressure typically signal and acoustic signal. Now if we zoom in a little bit more and look at more detail, here we're looking at the plunger cycle that says 3 cycles from static. We're looking at the time interval from 95 minutes to 96 minutes about. And this is just one falling through one joint. Now this is 3,500 feet from the surface, and that's the 112th collar. And this is the pressure recorded at the surface. So if I blow like that to my microphone, that's what you feel is a 2 psi pressure wave. Not very much. You don't feel that at all. Oh, you can't blow through a microphone. Anyway, this is a small amount of pressure. So you have to have a very sensitive pressure sensor to be able to see this. And this allows us to track the plunger and see the plunger falling deep in a well when we see these little pressure changes or the little changes in the acoustic signal, and that allows us to determine the position of the plunger, the fall velocity of the plunger, and then we can calculate the velocity of the plunger as it's falling down the well. This is another thing that you see here. This is the same well, plunger 3 cycles from static that we can look at later when we start looking at the data. But often when the plunger rests on bottom, you see a little pressure hop in the tubing pressure data. And that means the way that the plunger transferred off of the gassy fluid onto the bumper spring. And that's a little hop. And so that you see that about maybe half the time. So it depends on the well. You almost always see the plunger falling through the gas and see the collar spikes. Sometimes you see the plunger hit the bottom and see a repeat echo of the plunger hitting the bumper spring up the casing. That's a repeat echo from the bumper spring to the surface of the casing. And sometimes you see this little pressure hop to identify when the plunger's on bottom. So this is on bottom, this is on bottom. And we can zoom in and see that based on the data that we collect on the well. This is another plot here of, I don't remember which well this is. I didn't put the name of the well, but you can see that it says plunger hole. It says plunger hole in tubing deep. So there's the name of this example well. And what I'm wanting to show you is that when the plunger goes by collar 63 and makes this pressure wave, this acoustic signal, then the pressure wave leaves the plunger and comes to the lubricator and hits the microphone. It doesn't disappear at the microphone. It bounces off the surface and travels back down, hits the top of the plunger, And this is a repeat echo of the plunger going down the well. And this is a repeat again. So this is a round trip travel time to the depth of the plunger at collar 63. And we use that round trip travel time along with the depth to calculate the acoustic velocity. And there's our acoustic velocity for this example right here. So this is it right here for echo 65. And based on that round trip travel time, then we can calculate the gas gravity of the gas in the tubing. So this, the plunger is measuring the gas gravity of the gas in the tubing based on the acoustic velocity, and it does a weighted average of all the collars you pick and comes up with a weighted average of the collar echoes that you pick. Echo, echo, there's an echo, there's an echo, the collar, there's an echo. When you pick those, it summarizes them, does an average to determine the average acoustic velocity and then the gas gravity, the gas in the tubing that you're producing as well. So what else can you do? Well, you can find holes because the plunger has a certain weight. It's about 2 to 3 psi, which is the weight of the plunger divided by the area. So that's its weight is converted into a pressure. And when you drop the plunger from the lubricator past the pressure sensor, the pressure sensor sees the weight of the plunger falling through the gas. And the pressure below the plunger increases by 2 to 3 psi as it's falling in the tubing. And if there's a hole down in the well in the tubing, that 2 to 3 psi pressure will push gas out through that hole and equalize the pressure at the hole because of extra weight from the plunger. And then once the plunger goes by the hole, then we'll see that pressure increase, and we'll be able to identify the depth to a hole. Or if it sticks, we can see the plunger behave, see it stop. And so this is the pressure we're talking about. So here is the plunger, and we divide it by the area, and that in this case for this particular plunger is about 2.4 psi. And then here's that pressure drop when it falls out of the lubricator. That's a pressure drop of the plunger going by the pressure sensor in the well, and it was above the pressure sensor, and then when it goes below, then the pressure sees this change in pressure sensor sees this change in pressure of the plunger past the pressure sensor. So if you have the plunger held by a catcher, then the plunger's weight is resting and held against the tubing wall. And when the catcher releases the plunger, you see a sudden drop in pressure versus the gas pressure had to build up equal to the weight of the plunger divided by the area to release the plunger. So here the well releases the plunger itself by increasing tubing pressure, and here the auto catcher releases the plunger, or you release the plunger from the catcher. And so the behavior of the signal is somewhat different, where the well builds up the pressure, releases the plunger, and here the catcher was open to release the plunger. Now, here's a well down in the Barnett Shale. It's a gas well. Doesn't make much liquid, and in the well there's only about 2 psi of liquid in the well. And here we release the plunger, and now there's 5 psi of plunger weight and liquid in the tubing below the pressure sensor. As the plunger's falling down the well, this is elapsed time, this pressure is getting less and less and less until right here the pressure difference stabilizes equal to the weight of the plunger. And so from this point to that point, the plunger lift well is telling you that it needs a standing valve, because during shut-in all the liquid got pushed out and the plunger hit dry, and the casing and the tubing pressure equalized at the end of shut-in. So there's no liquid, the plunger hit dry right here. So this is a well that's telling you it needs a standing valve. It's telling you that the pressure there was maybe 2 psi is about a gallon, not very much liquid in the tubing, and then 3 psi from the plunger, and then here the liquid's all gone. So we need if we're going to try to deliquefy this well with the plunger lift, the tubing is set probably a little bit too high and needs a standing valve to keep the liquid from running back out the tubing during shut-in. And there's the well that we have that's on the examples on our webpage. So here's two examples of this pressure phenomenon. So here we drop the plunger right here. It drops, and this is where the example is plunger stops in a tight spot. And then you can see the plunger falling on the acoustic signal. And then when the plunger gets down to about 51 joints above the bottom, the whole 3 psi pressure from the plunger disappears. This vertical line means it suddenly stops. Well, here it suddenly started because it was released from the catcher, sudden drop. And here it suddenly stopped because it got trapped by a tight spot. And we see that. So we know the plunger to make the bottom. We can count the collars down to the depth. We know it's 51 joints off bottom. There's a tight spot right there. Now this one has a hole in the tubing. And so here we drop the plunger and it's falling down the well. And it says here it's 59th joint. And the 59th joint, you can see that as the plunger went by this little tiny hole, the gas in the casing started flowing back in, equalizing the pressure back where it was when you dropped the plunger, because this weight of the plunger pushed the gas out of the hole until the plunger went by and the plunger weight no longer on that hole. And so now the gas has to flow back in from the casing to equalize the pressure at the hole. And that's what's happening right here. So you can see the plunger go by a hole. You could have shot the fluid level and seen an upkick at the hole too. And there's an 1/8 of an inch diameter hole. This is a little itty bitty hole. And that little itty bitty hole caused the plunger not to come up 80% of the time, only about an 1/8 of an inch in diameter, little small hole. So it doesn't have to be very big to cause a big problem. Now this is a well that says the plunger hole is deep in the tubing. And what we see here is that, well, the green is the tubing pressure, no casing pressure. The red is the tubing pressure, the green is the casing pressure. And right there, the plunger goes by the hole and the pressure starts equalizing. And so we can see this pressure change by looking at the tubing pressure, and we identify the hole. The hole's at 8520, and it's only about 400 foot off bottom. They were having a hard time seeing this hole, and once they tracked the plunger, they could easily see the hole in the tubing. So this behavior it's just the way it works. The way the plunger is significant, and it shows up on the tubing pressure when the plunger weight's no longer being held up by the gas. Now, this slide shows us that we use the tubing pressure and casing pressure to calculate the gas volumes. And so this is the gas. In blue is the formation gas flowing into the well, and the green is the gas that goes down the flow line. And sometime in the future we'll include a discussion on this with the Fossenthal presentation. It increases your safety by knowing where your plunger is. If you're out working on a well and the plunger sticks a few feet below the surface, you can see what happens and not try to blow the plunger up dry and hit really hard. These high velocities can cause damage, and it's one of the things you want to know is where's the plunger at. You can see where the plunger is by tracking the plunger. So it's a pretty powerful feature. Now, this next slide here is we're going to talk about acquiring the data, and this is with the wireless equipment. And the wireless, we call this the base station. It's sitting on the back of the vehicle, and we see line of sight to the remote fire gas gun, wireless gas gun on the tubing on the lubricator, and we've got one also on the casing. And the wireless equipment lets you have 3 gas guns attached to the well, or 3 sensors, 1 gas gun and 2 pressure transducers. Maybe you want a pressure sensor on the casing or a gas gun on the casing. Maybe you want one on the pressure sensor on the lubricator. So this is some additional features we have available with the wireless equipment. We have to pick a well, and this Charlie Lambert A760 well is on the example data, and we're going to pick it. And if one wouldn't already on your computer, you have to create it. And you need things like production rates and tubing casing sizes, average joint length, end of tubing and C nipple depth, and the formation perforated intervals to track the plunger. This is the first screen once we go into plunger lift, where we have on the well. This is the well bore with the remote fire gas gun attached to the tubing, and we can preview and identify where the different sensors are attached. And then we also have another gas gun on the casing. And to start acquisition, we click there. But before we start acquisition, we probably want to open the valves and determine and make sure that the pressure sensor gas gun that we think we have is on the tubing and also the ones on the casing. So I'll be previewing this, and then I'll see the valve open. I'll see the pressure go up on the tubing. I'll be previewing the casing pressure, open the valve, and see the casing pressure go up. So I want to make sure I've got the correct sensors on the correct valve and use the preview to make sure that is correct before I start acquisition. We also have an optional sensor, like we can put on the separator, the sales line, if you're wanting to watch your pressures on the other side of your motor valve. So that's something you could possibly do. The preview is used to identify and make sure everything is hooked up right. So that's how preview is used. We have, in this case, two gas guns, and we're going to go into the different gas guns and zero the pressure on the gas guns before we start acquisition. And so we'll click on the details button and then get the zero offset of the pressure transducer before we start. And then once we'll have it zero before we apply pressure to the gas gun. This is just previewing the data, and it's saying we're previewing, and you see here that we open the valve right here between the gas gun and the well on the tubing, and we see this hop in pressure, and we knew that was the gun attached, and we see that it's hooked up correctly, and so that means we're okay, ready to start the test. We stop previewing, and well, before we stop, we want to make sure we're set the sample speed correct. So the sample speed, again, is 30 samples per second, typically for a padded plunger, because they typically fall slow, they seal well. And then probably 60 samples per second for a solid plunger. And then for a bypass plunger or two-piece plunger, 120, 240, or 480 samples per second. The two-piece plungers fall really fast, so you may have to go at 480 samples per second. You won't sample very long, but you'll have to sample fast, and you may want to try to sample 480 samples a second in your office before you go to well to make sure your computer is fast enough to keep up with the high-speed data before you run a test at the well. So now we stopped acquisition, we stopped previewing, we've got our sampling speed set, and we're ready to start acquisition. We click the Start Acquisition button, and the software starts streaming in the data streams from the tubing and the casing, the acoustic, and the pressure. If we click one of these little buttons with the arrow on them, this screen pops up and shows you the data all the data we've recorded so far from the beginning of the test. It shows you the current time, the duration, and the signal at that point. This is the last minute, and this is the current minute of real-time data streaming in. And so you can watch this during the acquisition of the data, looking for some kind of problem or issue in the well. Each of these points will blow this up to a full screen so that you can see the data that you're acquiring in detail. You really want to start the acquisition on the well before shut-in begins or before unloading begins, so that you have a complete cycle that you want to analyze. It works a little better for the software to acquire a complete shut-in cycle if you want to determine fall velocity from the beginning of the test till the end. Here we're counting collars, and we're looking at the screen. We're seeing that the plunger's fallen 1, 2, 3, 4, 5, 6, about 6 times the average joint length feet per minute, and that's a good estimate to see how fast it's falling. So I typically watch this acoustic tab and keep an average idea about how fast the plunger is falling. And here it's talking about how you might estimate that depth and the velocity to see how quick the plunger will get to the bottom. The plunger typically slows down as it gets deeper in the well. Here's the tubing pressure signal for the entire time period that we collected data. Here is the pressure drop right there when we open the motor valve. there's a button called annotate. And so the annotate button's purpose is to record things that happen at the well. And we can use those annotations to analyze the trace at a later date. Or you can identify problems that you see. When I first went out to track plungers, I just write information on a yellow sheet, and I'd have two or three pages of paper, and it'd be hard to go back and line those events up with 500,000 data points that I collect over an hour and a half. So the annotate button fixes that problem. We click on the annotate button, we click on a point that we see, and then something happened at the well. We say, well, the valve opened, or liquid arrives, or plunger arrives, valve closes, and so each of these events are marked on here. And these are default method events that occurred. You can also have a comment about something that's not a typical event that would occur, and those annotations can then be displayed on the trace or in the reports. So now we've got, anytime that you want, you can look at the annotate data and see what's going on with the well. It's a feature that has a lot of flexibility that lets you zoom in and look at a particular event, annotate, record a comment. So here we've got this the scroll bar at the bottom of the annotation. We can change the view on the screen. We have the casing pressure screen, casing pressure data, the tube pressure data, and the acoustic signal. We can use our magnifying glass to select a particular point and zoom in. We can change the time, the range of the time, and we can examine the data in more detail. Once we're finished collecting a set of data, we hit the stop button to stop acquiring data. The software says, "Are you sure?" and you say yes. We added the "Are you sure?" because sometimes if you just accidentally click the stop, it would stop before you were finished. It's happened to me a few times. And so we added a second stop to make sure that the real intent was to stop acquisition and it wasn't an accident. So you say stop, and then it says, "Are you sure?" Yes, you want to stop. You click it twice. Now this is an example of a data set where we left the equipment on the well overnight, and we acquired 20 hours of data. And this is a Charlie Lambert well A-760 on October the 8th, 2016. There's about 20 cycles here or so, not quite 20. There's 20 hours worth of data, probably 19 cycles. We sampled at 30 samples a second. There's 1,200 minutes of data. You can click on any point. You can analyze any cycle here you want to analyze. We'll look at that in a little bit when we look at the data. We thought it was important that we could, in the TWM software, we can only get maybe 8 hours. We can get much longer time periods with the TAM software for acquiring data. This is a wireless remote fire gas gun that we leave at the well, and we don't have to put in a plastic bag anymore. We've done some improvements on the gun. We've replaced the plastic button. We've replaced the connector for the charge fitting. We've improved the insulation, so it's pretty weatherproof. Not 100% weatherproof, but it's pretty weatherproof. We leave them out on the well now, and we don't wrap them up in a plastic bag. So that's a good feature that we've done. This is the way we arrange the base station and leave it at the well. We have the laptop inside a case that's weatherproof, a battery to keep it running, a laptop running. We have a fan on the bottom that cools the laptop, and an auto charger that keeps the laptop charged, along with keeps the base station communicating. We have on our help. If you click on help, the steps we just talked about are under help, and then there's a plunger lift manual. It's like a 150-page manual. If you click that button, and the manual is tied to the plunger lift normal example. The plunger lift cycle, normal cycle, is a cycle that's analyzed in the manual. So it's kind of a tutorial. You have the manual, that's a tutorial step by step, and you have the TAM software you can download from our webpage, and you have the examples that go right along with the manual that you can follow step by step to analyze. And that's available for you to use if you're interested in learning more about analyzing a plunger lift cycle. This tool minimizes your need for a wire line, lets you see in the well. You can count the collars down to where the plunger stops at the collar stop or the C nipple. It's a quick and easy way to identify problems in the well, and you can see when the plunger hits the bottom or not going to bottom. So with that, that's the end of the presentation, and I probably am ready for some questions if you would like.
Yes, we have a few questions only. I think we have like 9 questions so far. One of the questions is in slide number 6, I think you were at the beginning of the presentation, and if you were talking about having a half-inch pour valve or a quarter-tone valve type, where I assume that he was asking about where we connect the gas gun to the lubricator.
All right, so a needle valve is like a little pin that blocks the signal. So you really don't want to have a needle valve here. You'd like to replace the needle valve. You have one on the well with a fully opening valve. You want you don't want to tie the gun directly to the well, because that means you're going to have to shut the well in, and that will change the cycle and won't be stabilized conditions. So you would like to have your gas gun vertical so that any liquid that comes in during unloading will run right back out. Did that answer your question?
I guess it does. I think it was asking about the port size and what type of valve will we connect the gun.
Well, half inch or larger is fine. I mean, I don't think you should probably use much smaller than that, but a half inch, the whole half-inch valve is about 1/4 of an inch. It's not very big.
Okay, I hope that answers the question for Joel. So we have a question from Hector asking if the well must be prepared in advance to avoid different tubing sizes in the string.
Oh, well, if you have different tubing sizes in your tubing string, then a plunger won't seal. You can't run the plunger. So you're going to have either set your bumper spring at the taper at the junction and just run the plunger from constant diameter. I don't think there's any plunger that can run in 2 7/8 and 2 3 inch tubing taper.
Yeah. We have another question from Manuel. He's asking if there is no gas pressure to power the motor valve through the controller, what are the options? He's asking if a nitrogen cylinder, etc. What other options we have?
Yeah, you could probably pull the casing pressure or nitrogen cylinder. Those are 2 common methods.
Okay. And there's a person asking, Carrie-Ann, is this tubing and casing pressure measured at the wellhead, or is the tubing pressure measured at the bottom of the well?
Right. So this picture right here is a system connected to the well, and so the gas gun's at the lubricator, and the pressure sensor is at the surface on the casing, and then the bottom hole pressures are calculated based on the measured properties and the input properties of the oil, water, and gas in the well.
Right. Those both are surface pressures.
Yes.
We have a question from Mo Yunus. He's asking, could you explain dimensions of plunger and how much spacing between ID tubing and OD plunger? But then I think that was answered on the slide number 30, I think, where you have a comment on the you have an 8-pound plunger on a 2 3/8 OD.
Yeah. So the pads actually touch the well. So the pads are in contact with the tubing wall. A solid plunger or a brush plunger has a small gap, and as the plunger runs in the well, they check the OD of the plunger periodically, maybe every 3 months or less, to see if the wear has caused the plungers to leak too much. And so the brush plunger tends to wear out a lot faster than the solid plunger or the padded plunger. But the padded plunger is in contact with the tubing wall to provide the seal. That's very efficient.
Okay. And another question is, the wells that come up dry, is it better to add downtime and increase afterflow? And this is specifically for a well with 2 3/8 single pad.
Well, sometimes when the plunger comes up dry, it's not because there's too much energy. It comes up dry because the shut-in time wasn't long enough, or there's some kind of restriction in the tubing. So before you can really know what to do, you need to track the plunger and make sure it's getting to bottom. And then you need to, if it's getting to bottom, then you need to increase the afterflow time to bring in more liquid and reduce the energy in the well. But just coming up dry, it could come up dry for other reasons, which the two offhand would be, it comes up dry because there's no liquid. Which would be not enough afterflow. It comes up dry because it's not getting to bottom, which is a short rise. It comes up dry because it stops on some kind of debris or scale. So those are the three reasons I can think of, and there's probably more I can't think of right now. So you need to check it and make sure it's getting to the bottom.
I have a question from Ken asking if we can change the sample speed during the acquisition.
No. Once you set the sampling speed for a test, it'll say that sampling speed till you stop it. And so you kind of need to think about, before you start the test, to set the sampling speed based on the plunger type. So that's why I mentioned the 480 samples per second for the two-piece plunger. You can see the sleeve falling through the gas as long as the sleeve is above the liquid in the tubing. If you have EUE tubing and sample 480 samples per second, but if your computer gets choked with all that data and blows up after a minute or two, then that would be a waste of time. So the first thing you should do when you're sampling at high speed is sample in your office for the time, maybe the hour that you plan to track the plunger, and make sure your computer will handle all that data. It's a lot of data, 480 samples a second off of tubing pressure, casing pressure, and acoustic signal. It's a lot of data. So no, you have to set the time when you start the test.
I'm going to link another question from Manuel related to the same point. It is if you could mention again the sample rates versus the plunger type. If we have a table available, if not, just mention it.
Fast plungers, you have to sample fast because they go really quickly by the collars, and you can't hear them if you don't sample fast enough. It just looks like noise. So it's just you have to sample faster, and you also can't hear the plunger usually, probably over half the time, once it falls into the gassy fluid column.
Okay, Sergio is asking how to avoid contamination with liquids when slug arrives. And I'm assuming he's talking about the gas gun contamination.
Yeah, probably the gas gun, and that's a good question. I didn't even say anything about that. The first time I tracked the plunger, I didn't cock the gun and fill it with gas, and then when I took it off the well, it sprayed condensate all over me, and then I go, gee, that was a mistake. So whenever you track a plunger with a gas gun, you have to charge the gas gun, if it's a remote fire gas gun, to a pressure greater than, internal pressure greater than the maximum pressure you see in the well. So let's say your pressure goes up to 400 psi during the cycle, then you need to put more than 400 psi nitrogen pressure in the gas gun to keep the gas valve closed. Don't use CO2 because the CO2, if you do a test for like 4 hours, even though the O-rings are designed for CO2 gas, after 4 hours, the O-rings will get CO2 dissolved in O-rings, and then when you release the pressure of the gas gun to fire the shot, the O-rings will fizz as the CO2 comes out and they'll pop. So you should try to always use nitrogen gas to charge the gas gun to a pressure greater than the well pressure. And then also, if you have a compact gas gun, to manually lock the valve so it doesn't open. So yeah, close the valve before you track the plunger. You'll have a cleanup job when you after you get done tracking the plunger.
Okay. Thanks. We have another question from Yula Tang asking if we can load, that's related to the TAM software, if we can load the SCADA tubing head pressure and casing head pressure into the TAM.
No, the Echometer equipment is typically proprietary. We only use sensors that we know how they perform. And so we want to be able to use high resolution sensors to get high resolution data to track the plunger.
Okay, I have a question from Anil Yoshi that I'm guessing is related to the plunger lift system as a whole. It says, is it possible for deviated wells?
Usually plunger lift, you don't run the plunger past about 60 degrees, maybe 40 degrees, because the plunger won't come back up if you run it out too deep. So you have to be really careful about running the plunger deeper in the well than you can get the plunger to seal and come back up. So some plungers, padded plungers, if you lay them on the side, the pads in the bottom will collapse and then they won't go anymore. They'll just leak. So you have to be cautious about running the plunger deeper than 40 to 75 degrees. You can get some plungers to work deeper than that. But to find holes, you can see holes both by taking a fluid level shot. There's a dual shot method Carrie Ann's going to talk about in the future, and by the way the plunger going by the hole. But if the well is in a horizontal, if the hole's in the horizontal, then the plunger is not vertical anymore, and there's no plunger weight on the gas. So I don't think it will work if it's in the horizontal section of the well.
Okay. We have a generic question, and Aline is asking, what is the production range for this technology?
The technology that the main technology is seeing the plunger velocity falling in the well, and that works when the plunger is falling through gas, and it's very difficult unless the pressure is very high to see the plunger fall through the liquid. And so the primary use would be in wells that have some gas in the tubing. The tubing can't be completely full of gas, or you won't be able to see the plunger perform. So that's probably the main restriction. And so you can still record tubing casing pressure. We've got some data on some gas-assisted plunger lift wells, but we can't see the plunger because there's so much liquid, so much high liquid rate. Usually above about 100 barrels of liquid a day, you start to have the tubing fairly full of liquid and running some kind of continuous run plunger, and it becomes difficult to see the plunger because now the tubing is almost full of liquid. So it's typically a lower rate liquid well.
Okay, thanks. Mark is asking, can the software or sensors determine plunger wear and lifting efficiency?
That's a good question. So one of the things that we've added in the current version of TAM is a Echometer plunger performance coefficient, and the plunger performance coefficient is how fast does that plunger fall in your well. And so as the plunger wears, the plunger performance coefficient is going to change. It's almost like the velocity. It's almost like the fall velocity of a new plunger is what the plunger performance coefficient kind of is. Not quite, but it's kind of like that. And so the answer is, if you track the plunger frequently over a elapsed period of time, and you saw the plunger performance coefficient to be changing, then that would indicate that the plunger is wearing out. So the answer is yes. We don't have any data where we've done that. It would be cool to do it, because it would definitely, if you mic the plunger and you track the plunger, there is a definite relationship between the seal of the plunger as it wears and the wear of the plunger and the plunger performance coefficient. So yes, but we don't have any data that we could show that.
Hey, Dan is asking if you have any comments on wells with packers.
Plunger lift conventional plunger lift doesn't like packers. Gas lift likes packers. So a lot of times when your well starts to deplete, you want to convert the well from a flowing well with a packer to a well without a packer, because you want to use the casing annulus, and it's going to cost you money to take the packer out. So you might try to be low cost and shoot a hole through the tubing to use the casing annulus. If your packer is set very high above the formation, that's like setting your C nipple high, and it causes the cycle to not be steady, and the liquid will collect below the hole in the tubing to the top of the formation and slug in the tubing and kill your cycle. So you typically have to operate at much higher casing pressures, much lower load factors if you have a packer with a hole shot through the tubing to use a casing. It's a lot easier without a packer. Conventional plunger lift, it's a lot easier without a packer. So that's my comments about a packer.
Okay, Darrell has another question. Hypothetically, what would be the lowest borehole pressure required to move a plunger in 2 3/8 EUE tubing at 3,000 feet with a daily production of 15 barrels a day? That's a quick answer.
Well, okay. Well, see, what you should do is email Gustavo or me or Carrie Ann and ask us to send you that Fossil-Gall spreadsheet. It has rules of thumb and calculations of the spreadsheet, and we can tell you what the pressure required to bring the plunger up is. 15 barrels a day means you have to make quite a few cycles, but you're not very deep, so you can make fairly fast cycles because it's not very deep. Your unloading time, you just want to try to get about 750 feet per minute. So the plunger coming up at 750 a minute takes about 4 minutes to come up. So you could. The advantage is it's shallow well. You can make quite a few cycles, and you can if you divide your cycles up into if you have many cycles and you can still run your plunger, then I've seen casing pressures as low as 40 psi on a well that's 5,000 foot and work just fine. I've seen wells out in Durango with casing pressures as low as 50 psi, and those are deeper than that. So I'd expect you could probably run down to 24 psi surface casing pressure, 25 psi gauge pressure on a plungerless well, and get the plunger to run and possibly produce 15 barrels a day. But it'd be tough because you're gonna have to make lots of cycles to smooth out to make that liquid load small. The liquid load's what you're trying to lift, and you're trying to spread that liquid load out over many cycles, so the pressure's low. 15 barrels of liquid is like 1,500 psi pressure, and so you have to divide that 1,500 psi pressure into by the number of cycles to get how much pressure per cycle. And then at a minimum, you have to have a load factor of. We have Fossil-Gall's more exact, but a load factor of 2. So I mean, we can probably figure that out with Fossil-Gall, but the main it's possible in this well because you're shallow. That's the main benefit you have. Probably 25 psi and geez, a lot of cycles.
Okay. Well, Tyler's asking, when the plunger hits the standing valve and it's resting on bottom during a plunger track, is there a way to see if the standing valve is leaking?
Yes. Yeah, sure. I mean, absolutely. I mean, the standing valve, if it leaks pressure, it's gonna show you that the tubing and casing pressure are getting closer together. And so the slide I showed earlier, let me just go show you that. Let me bring up TAM here. And I don't see TAM. There it was right there. Okay, this is TAM, and the question that's being asked is, are these two lines getting closer together? And if they are, is there a standing valve in the well? And if the answer is yes, then the standing valve is leaking. And so if we go back over to this one well that says we're pushing, this is a well that needs a standing valve. We open this one up and we look at this data. This is in TAM. See, this distance from here to here is getting closer and closer, and then right there the distance is the same. And so this is an example. Let me change my screen just a little bit here because it's hiding the pictures of everybody. So when I look at this data here, the distance is liquid. This vertical distance represents liquid or pressure. And so at this point right here, the pressure is constant. That's the way of the plunger. And so from this point, from here, from that point right there, which is at 113, to that point right there, which is 129. So that's like 16 minutes, a little more than 16 minutes during shut-in. From the time the well shuts in to 16 minutes of shut-in, the liquid in this low liquid rate well is all pushed out. And if there were a standing valve in this well, it would be leaking. And so this is what you'd see. You'd see this pressure difference get closer together. So that'd be the answer. Yes, you can see that.
Well, we have several other questions. Let me pick one of those. One question says, can a salt block be identified between casing and tubing? And that's more related to the fluid level shot between tubing and casing.
Right.
So
a salt block, if it's completely blocked off, it won't move. And so the pressure, the surface casing pressure won't change during the cycle of the plunger. And so if you have a salt block, it reduces the area that you have in the casing. It provides less energy to bring the plunger up, and the casing pressure doesn't change because it's blocked. It's trapped. Now you can shoot a fluid level down the casing and release the plunger from the bottom. And if the casing pressure doesn't change and the liquid level doesn't move, it's likely due to some kind of blockage. So the behavior of the liquid level, behavior of the casing pressure, often indicates a lack of the ability of the gas in the casing to communicate to the tubing. And so that would be a salt block in the casing above the end of the tubing.
Okay. Yula Tang has a question. Do you know if there is any difference using Echometer in Gable gas lift facility plunger that has almost no shutting time and gas is continuously injected from gas lift valve?
Right. So one of the problems that we have with the so far, I've been talking to Jim Lee off and on about this for a long time, and he and I wrote that book on deliquefying gas wells. And one of the issues that we have is that when the plunge in a gapple well, there's liquids is filling the tubing, and so we can't see the plunger unless you start to intermit the cycle so that you have some gas in the tubing for the plunger to fall through. So we really can't see the plunger behavior in a well that the tubing's full of liquid. But Jim is working right now on a model that will predict it. So eventually we're probably going to have a model we'll talk about, because gas-assisted plunger lift is a pretty popular lift method. And so that's something we're very active about working on. I wouldn't be surprised if we don't have something we can try out here in the next month or so, maybe next 1 or 2 months. So yeah, we're working on
that. How can you compute the flowing bottom pressure using the acoustic trace?
Well, it's the way the gas plus the way the liquid column, and so and you measure the surface pressure. So you know the surface pressure, you know the way the gas, and almost always, if there's no packer and the casing valve is closed, the liquid level on a plunger lift well is always at the end of the tubing. So if it's not at the end of the tubing, usually there's a hole in the tubing where the gas is lifting liquid up the casing annulus and flowing back in the tubing through a hole. So it's just we know the liquid properties, we know the production rate. You tell us that, and we just use the standard pressure calculations to come up with it. So it's not a problem at all to calculate the pressure in the tubing. And then there's some assumptions below that about how much liquid of water and oil are mixed below the in the tubing.
Sergio has a question that says, what is the usage of the microphone signal in the casing? Can we just
Yep.
use the pressure sensor installed without the gun in the casing in order to reduce price?
Well, yes, absolutely. That's the normal way the test is run. So normally we run the test with a pressure sensor on the casing, and so what I was wanting to do with the two gas guns is I had a feeling, but no data to prove it, that when the plunger falls, you can see the signal on the casing gas gun when the plunger hits the bottom. So the reason why let me find that data here. I think it's right here maybe. Yeah, this is the data I want to talk about. So this data right here, we recorded the tubing acoustic and the casing acoustic, and this is the only well I've done that on that I can recall. And I wanted to see right here on this signal. This is the black is the acoustic signal. I wanted to see if I could see the pressure hop or the bang when the plunger hit bottom, and on some of these traces we can. So let me just show you that real quick here. I'm gonna expand this to be full screen here, and then I'm gonna take this magnifying glass right here and go into this data right here, and there's our signal. And what I'm wanting to know is is that an indication of the plunger being on bottom? And so I've got two microphone signals there. One's on the casing in red and one's on the tubing in black. And so you just see one black signal because the microphone signal from the microphone on the tubing is much louder than this quiet casing. So I'm going to go into the settings and make sure both of them are turned on. Both of them are turned on right there. And so I turn them on, and you still can't see anything. So I'm going to zoom into this right here, and I'm going to look. I guess it's in green, and sure enough, look, you can see a little spike right there in green and black. So the microphone on the casing heard the same signal of the plunger in the tubing, and so this is what I was looking for. I was looking for that. And then I was hoping that if I turn off the casing, I'm going to turn off this casing pressure reading here, go into this right here and turn off the casing pressure reading, turn this off, and then normally you'll see a little pressure hop. I don't see one right there, but in some of these tests on this well, I'd see a little pressure hop that would confirm that's the plunger getting on bottom. So that was the reason why we did that test, was to be able to see determine if we could see the plunger hit bottom by listening to the casing acoustic signal, and the answer is I think we saw it, and it didn't show up on every as you can see here, it didn't show up on every one, but that's why.
Okay, Lynn, I don't know if you have time for more questions or you would like to go through the examples. What do you want me to do?
Well, let's go ahead and ask me the question, and then pretty quick we're going to look at the data.
Okay, so we have a couple of more questions. Can we find, this is from Salinas, he's asking, can you find a washout valve on a gable well? That's assisted plunger lift well.
See, that gets back to the thing that Carrie Ann's going to talk about, the dual shot method. And so the answer is somewhat, when we had classes probably 5 years ago, if someone said, can you find the washed out gas lift valve, we would have said no, because there's no hole there. It's just a gas lift valve. But if you shoot the gas gun on one side of the casing or the tubing side of the well and listen with another gas gun microphone on the other side, the washed out valves will pass the signal through. And so you can. So that we've written a paper on finding washed out valves and bad check valves on gas lift wells with two gas guns. You shoot on one gun and listen on the other at the exact same time, and the valves that leak will pass the pressure wave through, and you'll hear it on the other pipe. So we can, if you're interested in that, we can send you eventually.
If you'll just,
go ahead,
you
Karen.
can type a quick message here, and I'll email you the technical paper, and then we'll talk about it. Email you the paper and a presentation that'll explain it.
Sure, that's good question.
I think we might have his email. Okay. Kind of a generic question is, what is the max well depth we can use with this kind of pumps or artificial lift?
Well, one of the things we said when we first started off was that it's not really depth limited. And so I have data on a well that's like 15,000 foot deep that someone tracked a plunger very clearly all the way to the bottom and could see the plunger. And so it's not the idea of you're not depth limited. You're limited based on the travel time, and every trip takes time. And so the longer time means less trips per day, and the less liquid you can carry per day. So a deep well means you have less trips. A deep well means you can only unload maybe 3 barrels of liquid instead of 10 barrels of liquid for a shallower well, because you can't make the number of trips to get the liquid out. So you're not limited by depth. You're limited by the time for the trips and how many trips you can make.
Well, let's do this last question asking, how can we know the corrosion between tubing and plunger?
I would say that the performance coefficient changes and the plunger velocity changes, and so what you'll see is that the plunger velocity is a function of the gas flow rate in the tubing. It's also a function of the seal, and so if you have a very corroded area of pipe, the seal is going to be poor, and the plunger is going to speed up. And so the plot of plunger velocity would be an indication of two things: gas flow into the tubing and seal or corroded tubing.
Well, we have a couple of more questions if you don't mind.
I don't mind.
Okay, well, can we use Echometer to find out if gas lift injection valve multi-pump injection? We have packers, and we can shoot from manuals.
We can find valves that are leaking, but we can't probably find the valves that are doing multi-injection. Now, multi-point injection, then another company, AppSmith, has a CO2 technique that they use where they inject a slug of CO2 and then it goes down the casing with the gas lift gas, and any multi-point valve takes some of that CO2 and back up the tubing. So you can push your liquid level down the tubing with Echometer equipment and shoot dual shots and find leaky valves, but you can't do it while it's producing the well.
Okay. On gas-assisted plunger lift, does compressor need to be off to minimize the noise? Will that matter?
You know, that's a good question, and so you know the compressor makes noise, and so if we're trying to track a plunger, and it's being picked up, the way it's being picked up on the tubing, sometimes you may not be able to. It may be too noisy. So, you know, compressor noise could be a problem tracking the plunger down the tubing if we're getting that noise in the tubing. But if it's on the casing, I'm not sure it's going to be much of an issue. So that's, yeah, I don't know how to answer that, because I don't think that for sure if it's being picked up on the tubing and it's noisy, you just won't be able to track it.
Okay.
I'm gonna minimize this. What's the next question? And I'm gonna go pick up a well here.
One more question is, control valve closed, and line pressure declines. What possible cause of it? What's the possible cause of it?
Well, line pressure declines means that, so that means you have some kind of, the flow is going away from the motor valve down the flow line. The line pressure is dropping because of, um, could be a leak on the outside between the separator and the motor valve. It could be something like that, or maybe you're pulling gas off that line there to run something. I mean, but normally we have a troubleshoot spreadsheet. So if you're wanting to, I've got 2 Excel spreadsheets that other people put together that list different problems and show what you should do. Like, do this, check this first, check this second, check this third. So if you're interested in me sending those 2 troubleshooting spreadsheets, one's for watching the well from the office on the control system, and the other one is going out to the well to inspect the well, then email me at lynn@echometer.com and I'll send you those 2 spreadsheets. So, or anybody else should have those. So anybody can send those. So, but we have those spreadsheets. So is that the last question, Gustavo?
Yes, so far that's the last question.
Okay, well, let's talk about. So on my screen here, I've got the TAM software opened up, and I have gone into. Let me just do it again. I go into pick a well, and when you get the data files off of the Echometer webpage on the Ask Echometer, then those when you load them into TAM by default will put the first presentation on acoustic and downhole markers in this folder, and then the second presentation on mechanical friction in this folder, and then the presentation today will be the third presentation on plunger tracking, conventional plungers. And so they'll be put it on your computer, and then inside when I click on the plus inside Echometer Online plunger tracking, then there's 1, 2, 3, 4, 5, 6, 7 examples. And so the example I want to talk about first is the one that we put in the manual. So if you go into the plunger lift normal cycle and open that up, and then go to the plunger lift well right here, then this is the plunger lift well, and I have the casing pressure turned off. So let me turn the casing pressure back on. So I go into settings and click casing pressure. And so now I've got the casing pressure turned back on. Let me just kind of show you a few features, and then let me show you first the manual. So this is the well that the manual is based on. So if you go into utilities, not utilities, help. If you go into help, you click on help, then the help appears on your screen, and it shows us that there's a plunger lift manual help. And if I click on the plunger lift manual help, then this manual is 128 pages. I thought it was more than that, but 128 pages, and around page 50 is where we go through step by step on how to analyze this data. And so what's my point? My point is that on your computer now, if you download TAM, you have the manual and the data set that you can use to go through and learn about this software. And you can ask us questions, you can email us questions. You got a data set that's been collected, and it matches up with the manual, and you can, if you're interested, learn about just that with just that method. Now, I think that's a pretty powerful tool that you can then use to understand plunger lift. We've got 4 or 5 or 6 examples here. They're really good examples. Plus, we have this example that goes along with the manual. Now, when you look at this, when you open up plunger lift and you see this screen, it's telling us that we have 92 minutes of data here. This screen right here at the very top is the entire data set. So if I take my mouse and I put my mouse right here and I drag this line over, it changes what I'm seeing on the screen. If I drag it to right there and then drag this right here, I'm gonna see a detailed view of when the plunger comes up. And so right now, all I can see is this black fuzz here, the microphone signal, and it hides the tubing pressure in the background. So an option to fix this is to go into this and then move the tubing acoustic move it down, and then that will make the tubing pressure be shown first on top, and then the acoustic behind it, so we can see that. So there's a lot of flexibility in the way this stuff is displayed by what? By looking at the settings. Now, these dashed lines right here are the annotations that we mark this trace with while we were acquiring data. So when we were acquiring data, we saw the liquid arrive and we saw the plunger arrive, and so we put those annotations on this screen, on this data set, so that we could mark this and know what happened right there for later analysis. And so this is the entire time right here, and I can move through this time and look at it. I can change the time right here to a certain time interval. Here it's 10.826 minutes. I can see when it started. I can see when the test ended. I can see the duration of the test in time. I can see my sampling speed. If I click on the graph with my mouse, then there'll be a pointer that comes there, and that's the time that I clicked on the graph, and these are the tubing and the casing pressure readings at that time. And I can move this line around to whatever I want to examine on the trace. This will zoom the trace out completely to the full screen back to all 92 minutes of data. And so there's all the data. When I look at this screen and I go to the report, well, let me go a little farther. So if you want this data to go into an Excel spreadsheet, you can come down here and click on the export button, and all these data points can be exported into a file that you could then use to do whatever you want with. If you want to embed the graph in a report, you can right click on the graph and copy the image to a clipboard, and that could be pasted into Excel or Word or a Notepad, whatever you wanted to do. So any of the data that's on the screen, any of the data, the plots, any of the pictures can be exported out. That's all available. If I go into analyze the cycle, and this is the cycle I'm going to analyze, I can click cycle and I can say add a cycle. And so this is the cycle I just added, and I go to define the cycle, and this screen pops up, and I'm going to say the valve. Well, I'm going to first of all, I'm going to turn the casing pressure back on. So there's my casing pressure, tubing pressure, and acoustic signal. And the cycle begins right here when the valve closes. So I say valve closes to begin the cycle and say yes. And so this is the beginning of the cycle right here. And I'm just going to get kind of close. And this is the end of the cycle right there. And then this is the right there, that's point B when the valve opens. And so those aren't very close. So what I'll do is once I've got those points picked, I'll put in like 5 minutes of time and make the window small. I'll tab out of the field, and now I can see that I didn't pick it very close. So I'll click right there on when the tubing pressure sensor motor valve open, the tubing pressure starts to drop. Then I'll click back on the valve open, and I'm going to move it over to when the pressure starts to build and the microphone signal start to get quiet. And that's when right about there is where the shut-in began. You can see the signal of the plunger falling by the tubing collar recesses on the EUV tubing. And then I'll go to the cycle limits. And this has got the annotation shown here. And so if I go here, I'd say, I'd say plunger hits liquid, and I come down here and pick the annotation. Well, let's do this one first. Plunger on bottom is right there, and let's go pick plunger on bottom. So I'm going to go pick 2 and say plunger on bottom and apply to the marker. And it just, so if you annotate the cycle out in the field, you can use those annotations later on to identify those events back in the office. And so the next one is liquid arrives, and I'm going to put that one to liquid arrives right here, and then apply to marker. And then the next one is plunger arrives, and that's right here. And if I want to see it in more detail, let me zoom in and show you what's going to happen here. So there is the annotation. I say I want to make plunger rise right there at the annotation, and I select that and I say apply to the marker. And now I've got my cycle selected, and I'm going to go to plunger fall now, and so there's the plunger falling down the well, and that's when the motor valve, when the plunger left the lubricator. So that's the first collar it went by at the surface times 0, and then here is the next one, and then it starts to jump to the next collar automatically, and I just say add a collar, and once it's being pretty consistent and the signal is really clean, I can say auto select, and it'll select all the rest. And it went all the way to the end, and sure enough, it's got all the collars counted, and here the fall velocity in the gas, you can't read it, it's 168. The fall velocity in the liquid is 38.9, about 40 feet per minute. If I blow this fall velocity trace up and look at it in more detail, here's the fall velocity plot. It's on top of that other one. And if I click on a point like right here, then the table rotates to that point. It's collar 64. It shows collar 64 here. It says we're at a depth of 1,513 feet. The fall velocity is 227 feet per minute, and we're at that clock time. Well, I don't really want clock time here. I want minutes. So if I go down here and click on this clock, well, maybe not there. I want it in minutes. So if I go back over here and find this right here, I can change the time to minutes. So there I've got it in minutes. Now I go back to the cycle analysis, pick this cycle and go down to define cycle. I've already got that picked. Go to cycle limits, I've got that picked. And now notice it's minutes on the axis. I go to plunger fall, it shows minutes. And here's the column in minutes, so it automatically converted it into minutes. I can change the time scale, I can change the depth scale to whatever units that I want. And I bring this graph back up here, and here's the graph. And if I click on this one, I don't like that one. I think it's not correct, because see, look, it's not in this trend. It must be it's an outlier. So why is it an outlier? Why doesn't it match up? Well, if you look right here, the plunger went by the collar and made two noises, and it went there, it only made one. Here it made two, and it's the second one. And there's the first one, and there's the first one. So the real problem starts over here. So if I take this one and move it to right there, and that one's on the first one, that one's on the first one, and that one is on the first one. Now that little point moved back up into the body of the data. And so, you know, sometimes you might have to fine-tune the automatic pick. These are automatically picked. Anyway, that's just an example of counting the collars. I've got the collars counted. Then I guess the next thing is do the gas properties. And I'm going to go into the data and move down to about, hold on, look. Echo, echo, echo. And they're really close together, hard to see. So I'm going to go down to about collar 60, where they're spread farther apart. And so now I can see a double kick, and then I'm going to pick that one right there. And I got that one added. And now the acoustic velocity in this gas is about 0.82. It's a little bit less than that, but I can pick another one, average amount. But this is an example of round-trip travel time to the depth, and that gives us the gas gravity. Once we have the gas gravity in the well, we can go into the analysis of the data. And so here's our analysis of the well. We can set this to, let's say, 3 second steps. And I can say replay it. And so here's the plunger falling in the well, and here's the real-time calculations changing. Here's the flow rates. Here is the plunger depth, plunger velocity, bottom pressures, liquid in the tubing, percent liquid. And then if I go to the analysis plot, there's the graphs of that same data. These are, you know, real-time, not real-time. These are calculated from the data that we just acquired on the well, and it shows the plunger falling down the well. And this is pressures, and I can stop this if I want. and slide it to right here, and I can say, okay, right there, the plunger's fallen to the liquid, and it's fallen on average about 38.95 feet per minute. So I think I'm about running out of time, but that's a quick review of the data. You're welcome to look at it and email us questions if you have additional questions. Hope you enjoyed this, and I'm going to let Carrie Ann wrap up.
Oh, sure. Thank you, Lynn. And thank you all for joining us. And we certainly have enjoyed the questions and interactions. So if you have any follow-up questions, please feel free to email us. You can respond to the registration email if that's easier. And we'll always welcome your phone calls and emails. The recorded video of this session will be available on our Ask Echometer webpage, and I put a link out there on chat for you guys to see that. You can also download a PDF of today's presentation, and then of course the data that Lynn has just gone through with the example. Next week's session the topic will be on static bottom hole pressures, and the presenters will be Dieter Becker and Dr. Tony Podio. So if you are already on the registration list for the weekly sessions, you'll all automatically get an email from me with each week's session link. If you haven't sent your email in, you can just leave a comment here on the chat if you'd like, or go to the Ask Echometer webpage, and there's a registration link that you can click from there. So we appreciate your time today. We're so glad that you joined us, and we look forward to seeing you guys again next Wednesday. And have a great week.
All right, talk to you all later. Thanks.
Thank you so much.
Yeah.